So let's talk about the Doppler effect of light. We'll see that this Doppler effect of light is related to time dilation or length contraction, but slightly different. You have to think in slightly different ways to figure out the Doppler effect of light. So let's set up the problem here. Let's say that there is a radiation source which emits light of a certain frequency, omega 0. Okay, so that omega 0 would be kind of the true frequency of this light, because this radiation source is at rest, and then it's radiating frequency omega 0. But now, let's say that we are observing this radiation source, and in our reference frame, this radiation source is, let's say, it's moving, x prime and y prime, and this radiation source is fixed in that reference frame. So this omega 0 would be the frequency that's measured in the rest frame of this radiation source, which is moving at velocity v of the radiation source. Now the question is, when we observe the light coming from this radiation source that is moving at velocity v, what would be the frequency? Will it be the same as omega 0, or would it be different? Well, it would be different, and that's called the Doppler effect of light. So how do we figure it out? So let's it's not really that difficult. Let's figure it out. And the thing about Doppler effect is that it's dependent on whether the radiation source is moving away from us or moving towards us. So to be specific, we will consider the radiation source that's moving away from us, and we can figure out the answer when the source is moving towards us, once we figure out the answer when it's moving away. In order to proceed, let's actually stay in the prime coordinate for a little bit. So let's go to this rest frame of the radiation source, and let's make a plot. Let's make a plot of the wave coming from the radiation source. So this is like the electric field of light, and this horizontal axis is time, t prime. And let's assume that, for example, we stay with the radiation. We measure the light amplitude coming right from the radiation source at the position of the radiation source, and just make a plot from of the electric field. So because we assume that this is a single frequency light, the light will be sinusoidal. It will look like this cosine curve, for example, and if this time is 0, then this time will be t, the period, capital T, and let's call it t0. Okay, t sub 0. That's the, and that period t0 will be related to omega 0 by this well-known relationship, 2 pi over t0. So now the task we have at our hand is to transform this, let's say the two events here. The first event, the first maximum of the amplitude, and the second maximum of the amplitude, to the events in the unprimed coordinate system that corresponds to this rest frame. Okay, so we are observing this this event from this rest frame, which we call x and y and t and etc. And so now let's say that during these two events, between these two events, delta t prime is t0, t sub 0, as we defined here, and as we defined here, delta x prime is delta x prime is 0. Because when we make this plot, the position at which we record this light amplitude is fixed. Well, otherwise this kind of plot would not actually make any sense. So delta x prime is 0. So now we translate these delta x prime and delta t prime values using the Lorentz transformation. And what are those? Delta t equals gamma delta t prime minus, actually it's plus in this case, plus v delta x prime. And then delta x equals gamma of delta x prime plus v delta t prime. And again, I'm using the unit c equals 1 in these equations. And so if you plug in those values, then well, it's very simple really. This is gamma of t0, and this is gamma v of t0 also. So does that mean that the new period t that you measure in this rest frame is gamma times t0? No. The problem with that is that the two events that are connected by delta t, actually they are not happening at the same position here. So that delta x is different. What that means is that the following. So let's say this is event 1. Let's say event A. This is event B. Those two events happen at the same position in the prime coordinate system, but if we were observing this this light source and the light coming out from it in this rest frame, then event A and event B clearly happen at different positions. So let's say event A occurs at a certain time measured, and then event B happens at a certain other time, which is given by the time difference is that this delta t, but also this equation says delta x. These two occur with delta x, which is given by gamma v times t0. What this means is that the time difference between these two events cannot be the period that we measure. How do we actually measure period for a wave? Well, when we measure the period of a wave, we must focus our attention on one spatial position, and then measure the wave amplitude and see how it repeats. And so we must observe this delta t when delta x is 0. So what that means is that, well, the light that comes from, let's say that we are observing, let's say for our convenience, let's say that we are recording the light amplitude at this very position when the event A occurs. When the event B occurs, that's after delta t, but now that doesn't correspond to the same position as the position of event A. In order for the light amplitude generated by event B to be recorded at position of event A, what happens is that we must wait for that light to arrive at the position of this delta a position of event A. So what that means is that the period that is measured in this unprimed coordinate system is given by this guy right here, gamma t0, which is the time difference here. But we must wait some more, because why? Because the light source is moving away from us, and so there is this separation in space, delta x. So we must wait some more time, which is gamma v t0 divided by c, but now we're using the unit c equals 1, so that's the period that we measure in the unprimed coordinate system. So then this t becomes gamma times 1 plus v of t0. So now what is the angular frequency? Angular frequency is 2 pi over t, so that means omega equals gamma 1 over gamma times 1 plus v times omega 0. So that's the Doppler effect. So let me write that. With c included, and if we include the c, then it becomes gamma 1 plus v over c omega 0, and then I might also throw in the negative sign there, and so what it is that plus sign corresponds to the case when the source is moving away from you, and minus sign corresponds to the case when the source is coming towards you. So for the case when it's coming towards you, you can do the same derivation as in here, and you can verify that the sign here becomes negative. And if you look at this expression here, the expression there, you can show easily that that expression becomes, let's see, square root of so gamma was 1 minus v square over c square, so that means this is c v plus minus c minus plus c. So the signs upstairs, minus here, plus there, corresponds to the case when the source is moving away from you, and plus sign here and minus sign there, the signs downstairs correspond to the case when the source is moving towards you. So you can see that when the source is moving towards you, this factor here is greater than 1, and which is reasonable. And when the source is moving away from you, these signs here, minus and plus, corresponds to the case when this factor is less than 1. So the omega is smaller than omega 0, which also makes sense.